Okay, so let us begin. If you have any questions about yesterday's material, please stop me just now before we begin. Or you can also ask me in between. Okay, so we started with some motivation for the whole week. And there are three goals. Yeah, we want to classify representations and representations of quivers. However, for the first thing, okay, Damotiran is saying it is fine as I'm new to this topic, quite difficult to understand in time. Okay, what particularly you found hard, you can tell me and we can perhaps repeat certain things. Yeah, if you say something specific, then that would be good. Okay, Riju is also here. Thanks for switching on the camera. Right. So let's. Sadanand, how is the speed? Then Sushma was also there talking yesterday. So please give me some feedback whether the speed was fast, slow, and
Speed was good. I like the lectures. So
huh?
everything
Yeah,
I
lectures
was
are
able to
perfect.
follow. Yeah, yes,
Lectures are
everything I was
perfect.
able to
Okay.
follow. Yes.
Okay. Thank you. Okay. Let's proceed then. Yeah. So our first goal is of course goal one. Every single thing that we want to do, every classification problem was phrased in terms of the word quiver. However, we want to replace the word quiver by finite dimensional associative K algebra. The presentation aspect of this particular type of representation theory. And what we did yesterday was we started with some language of associative algebras. So what's an associative algebra? It's simply a ring, which is also a vector space. We looked at some examples. And I'll come back to these examples. We looked at the concept of the Jacobson radical. And then we moved on to representations slash modules of such algebras. And we said that if we are working with finite dimensional algebras, then all the module categories which we can define, left modules, right modules, they are all abelian categories. So we have direct sums, kernels, co-kernels, etc. And then we looked at the notion
So
of a
here your
local
field
algebra.
is algebraically closed or any field?
Yes, I'm going to assume throughout that field is algebraically closed. However, I'm also pointing out some locations where the proof actually uses that it is algebraically closed. So for example, this one, that in general, for a local algebra, what do we say? One of the equivalent conditions is that A mod the radical of A is isomorphic to a field. However, if the field is algebraically closed, then that field is actually K. Yeah, that we showed, that we saw yesterday. And the only idempotents in this case for finite dimensional algebra are 0 and 1. In fact, if our local algebra happens to be a finite dimensional algebra, then in these 5 equivalent conditions, we can also add one more condition, namely that the only idempotents are the trivial idempotents, namely 0 and 1. Okay, so that we can add over here. And we looked at the criterion for indecomposability, that M is indecomposable if and only if the endomorphism algebra is local. Okay. Then we started with path algebras of quivers. So quivers are, as you know, 4 tuples. Yeah, those 4 tuples are Q0, Q1, and the source and target functions on the arrows, and the lazy path and a positive length paths. So both those things are paths, and we take paths as the set of generators, and then we describe the path algebra. We looked at some examples, and let me go to the set of examples here. So we saw that the algebra K can be thought of as the path algebra of single vertex quiver. Then Kx is with the loop quiver. Then Kxy is with I mean kxy, this one, yeah, the non-commuting polynomial ring in two variables, in two non-commuting variables, that is with two loops and the upper triangular matrices and lower triangular matrices with some orientations of an. And this slightly non-trivial example also, we saw that there was some orientation of A3 which gave us this. And we ended with the question that what to do if we are talking about polynomial ring in two commuting variables and matrix algebra. These two we haven't touched so far. Okay, so this is where we ended last time. Anybody wants to answer this? Yeah, the how to get this matrix ring, for example. Maybe there was some discussion in the tutorial yesterday, but if you have had time to think about it, then perhaps you can also speak now.
So for matrix algebra, do you want to use Morita equivalence?
Yes, we will use Morita equivalence. Correct. Yes, that's correct. And for people who don't know, I will cover that part soon. Right. And
Thank you.
thank you, Dibyendu. So what we saw yesterday, yeah, I think we also have this the concept of an opposite algebra, yeah, AOP, where we simply invert the multiplication. And then can you tell me that there is also a natural operation? Let us begin with that, yeah. So suppose Q is the original quiver. So Q is the, wow, I'm not sure why this is happening. So if Q is the original quiver, which is Q0, Q1, source and target, if we actually simply change these functions, yeah, so we take the same set of vertices and arrows, but we change the source and target of the arrows, then actually we will get the corresponding algebra. This is KQ and this is KQOP. And what happens that this algebra, the opposite algebra of this, is isomorphic to the path algebra of the opposite quiver. These types of dualities we will talk about several times. Yeah. Any question? Yes.
Yeah. So yeah, in the second case, I mean that you are reversing the arrows, is it?
Yes, I'm simply reversing the arrows. Yes, we simply reverse the arrows and then it is isomorphic.
Okay.
I mean, see, Q1 is still the set of arrows and I'm simply I'm making the target the source the target. So we are reversing the direction of the arrows. Okay, so this way we can see one natural example of an opposite algebra. But it is also a path algebra. So opposite algebra of a path algebra is also a path algebra. Then we looked at the Jacobson radical of this. We have to come here and we described what the multiplication was and we looked at some examples and saw how in the finite dimensional case we can look at it through matrices. And hopefully you are easily convinced that Q is acyclic if and only if the dimension of the path algebra is finite. Because there are no cycles, no infinite things. So therefore it's easy. We looked at one example, the loop algebra, KL1, and there it was the polynomial ring, which is obviously an infinite dimensional algebra. Okay, so what is the unity in this particular type of algebra? If we are talking about a finite quiver, then the unity is just this, the sum of all the lazy paths. That is our unity. Okay, so let us look at a particular example maybe. See, what I'm talking about is simple. Summation lambda pp. This is our arbitrary element. And I'm saying take summation ei, where I is a vertex. what will happen? For each lambda pp, we are going to take this summation. So this will be a finite sum, as we know. It's a vector space generated by these, where this as a basis. So inside we will have lambda pp multiplied by summation ei. Yeah, and then we are taking a bracket outside. Now, can somebody tell me when will this be non-zero? P times summation ei, when that will be non-zero?
Its source of P is EI.
Exactly, source of P is ei. Otherwise, it will be zero, right? And that's why this will only survive once, exactly once. All other EIs are going to annihilate that element. So therefore, this will actually just be the finite sum of lambda pp. So hopefully I convinced you that these EIs, summation of EIs is the identity element. Yeah. Okay. So these EIs actually have some very special property, and I'm going to show you just that. So we missed this part yesterday because we wanted to talk about something more interesting related to quivers. So idempotents and how they are related to direct sums. This is again some background material. So let me recall that an idempotent is an element whose square is itself. We saw this yesterday very briefly. And we say that a set of idempotents is, yes.
So
Irfan, yeah.
Yes. Are we concatenating paths from right to left?
Yes, yes. I think you were absent yesterday, so that's why you are.
Yeah. Right. Sorry.
Right.
Sorry.
Yes.
Yeah. Go ahead, please.
That's correct. Okay, so we say that a set of idempotents is an orthogonal set of idempotents if whenever you multiply two elements, then either it is like ei ej is equal to ei if I is equal to j, otherwise it is zero. A simple orthogonality condition. So Kronecker delta comes into picture here. And an idempotent, we say, is a primitive idempotent if it cannot be written as a sum of two non-zero orthogonal idempotents. So E is equal to E1 plus E2, where E1 E2 is equal to 0, E2 E1 is equal to 0. That should not happen. Okay, so this is our definition of a primitive idempotent. And naturally, like if you know one idempotent, then you obviously know the other one. It's simple algebra. You must have seen this in commutative algebra or ring theory course, that if E is an idempotent, then 1 minus E is also an idempotent. And 0 and 1 are always idempotents. Our algebras are unital. So 0 and 1 are idempotents. We call them trivial idempotents. Yeah, the non-trivial ones are the other ones. And why we are doing this? We are doing this all because the lazy paths, yeah, those lazy paths are actually idempotents. In fact, they are primitive idempotents. And they are clearly orthogonal to each other. ei multiplied by ej is 0 if I is not equal to j. Okay. So what happens if E is a non-trivial idempotent, then we have a direct sum of the left regular module as the ideal generated by A, direct sum ideal generated by 1 minus, E, and ideal left ideal generated by 1 minus E. If this idempotent happens to be central, which means it commutes with every other element in the algebra, then this is also a decomposition of rings as a direct sum. Otherwise, I mean, we will mostly be concerned with this kind of decomposition, that we have the left regular module, A thought of as a left module, and we will be concerned with this.
I had a question.
Yes.
So if these are central, then can we say that this would actually be a projection, as in, I mean,
Projection onto individual algebras.
Individual components as a ring
Yes.
projection, I'm thinking.
As a ring
Because
projection. Yes, yes. That's why it's direct sum. No, wait. I think in
No,
rings,
I mean,
direct sums, sorry, Cartesian product and
see, I mean, this is a direct sum as a module, but I'm saying that if you're saying it's central, then it would be a direct sum of rings, right? So
yes, it will
can
be a
one?
direct sum of rings.
Yeah. Okay. So, I mean, I'm just thinking, I mean, there's a possibility that one can write identity as E1 plus E2 plus dot 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 En, where all of these are primitive idempotents,
Yeah.
like how we normally do when we are doing Jordan decomposition. We'll be breaking things down into the idempotents for the various invariant spaces. Now, can one have something similar coming over here? Like instead of having a sum as just E1 plus, I mean, AE1, AE plus A1 minus E, you're having AE1 direct sum AE2 like that?
Just hold on for a moment. Yeah, at the bottom of this page itself, I have written that. I'm
Okay.
just trying to go a bit slow. Yeah. Okay. So this one as direct sums of modules is what we are mainly interested in. And in fact, if you can break a module as a direct sum of two modules, then you will get idempotents in each one of them, such that the unity can be written as sum of those two idempotents. And this mi is indecomposable if and only if ei is primitive. Obviously, I'm not going to prove these results, but hopefully you can believe that indecomposability has to do with primitivity. In fact, how do you check whether some idempotent is primitive or not? You simply, this is a criterion, this is a necessary and sufficient condition that EI is primitive if and only if the algebra EI has only non-trivial idempotents. Okay, so let me just make this I. Yeah, EI has only non-trivial idempotents. And if we are working with a finite dimensional algebra, then there is a complete set of primitive orthogonal idempotents, but a finite one. Yeah, so which means there are idempotents even e to en of such that one can be written as a sum of idempotents, and the left regular module can be written as the sum of these indecomposables, AEIs. We are going to call these AEIs the projective modules. Yeah, we'll see that soon. Okay, so yes.
I have a small question here. See, so this primitive corresponds to the simple representation inside a group algebras, and the centrals are the isotypical components.
Projective.
Okay.
Yeah, primitives correspond to indecomposable projectives over here. And don't talk about group algebras, we are not doing that yet. Okay, so basically, yeah, maybe we were here. We took a detour at this point that unity is the sum of all the idempotents. So sum of all they are idempotents, and they are actually primitive idempotents we just saw. So therefore, this indecomposable module Pi, which is the left ideal, which is generated by paths starting at I. Yeah, we are just going to call this the left ideal generated by EI. If you remember, then Upendra mentioned this already. Yeah, he gave a description of the projective module at vertex I. And what he did was he simply took all the paths from I to J. And that was the basis of that particular vector space. So I'm not saying anything different. I'm just expressing it in a different language. This is the left ideal generated by EI. And on the other hand, dually, the injective module is the right ideal generated by EI. Yeah, so it is the right ideal generated by paths ending at I, because of how we are writing things.
I have a small question here.
So,
So, are you claiming EI or primitive because the left ideals are indecomposable, or EIs are
you
primitive
have a
for some
proof.
other?
Yeah, you can prove that PI is indecomposable the way that we have
Because
defined
of
it.
that, you are saying EIs are primitive, or you have some other reason for
So we
EI
should
being
prove
primitive?
that PIs are indecomposable, and
Uh-huh.
therefore, by using that theorem, we can show that
That
EIs
okay.
are
That
yes, yes. But I'm
thanks.
not doing these proofs.
Yeah, he did it. Yeah, EIs are indecomposable. Okay, that's what it.
Right. Okay. So now we are interested in understanding what is the Jacobson radical of the path algebra. And in order to do so, we need to understand what are the maximal ideals. So maximal ideals are precisely the ideals which are generated by all the paths except one zero length path. We cannot leave out something else. Okay, if you leave out one longer path, then you are actually leaving out all these subpaths of it, proper subpaths of it as well. So therefore, if we want it to be maximal, then you can only leave out one generator of length 0. Again, I'm only trying to convince you over here that these are ideals generated by all paths except for one lazy path. And therefore, what will be the intersection of all the maximal ideals? Well, they will be ideals, that will be the ideal generated by all positive length paths. Because one lazy path is missing in each maximal ideal, so you simply remove all of them when we are taking intersection. And the common things will be the ideal generated by all other paths, all positive length paths, or equivalently, it is a two-sided ideal generated by all the arrows. We are going to call this RQ. Yeah, this is the so-called arrow ideal of Q, RQ. And this arrow ideal is a graded ideal. Our original algebra is also graded. Yeah, you have the zeroth grade component is the one generated by EIs. Then first component is the one generated by arrows, and then squares of arrows. Yeah, I mean RQ square and so on. Length 2 paths, length 3 paths, and so on. So this grading of the ideal is here that RQ is KQ1 direct sum KQ2 plus dot dot dot. If it's finite dimensional, it will be only a finite direct sum. Otherwise, as vector spaces, yeah. I'm not saying as an ideal, just as a vector space, I'm decomposing it. KQM is the subspace generated by paths of length M. And this gradation actually helps us to understand what is a power, a finite power of this arrow ideal as well. It is simply the direct sum of KQM where M is at least L. Yeah, this particular direct sum is closed under multiplication by arbitrary elements on either side. Okay. So what can we say about this? Well, if Q is acyclic, then acyclic basically means that there is an absolute bound on the length of paths in Q. Now, the path is not of infinite length. There is an absolute bound, which means the arrow ideal is nilpotent. Right? Because beyond a certain point, there will be some L such that RQ to the power L plus 1 is 0. So therefore, what happens? And moreover, KQ mod RQ is what? As a vector space, it is just K to the power the number of vertices. So if you remember a result from yesterday, yeah, let me take you back to that result. Yes, the result is here. If a two-sided ideal is nilpotent and the quotient, the corresponding quotient algebra is isomorphic to K to the power N for some N, then actually it equals the Jacobson radical. And I'm just going to use that result to conclude this, that the Jacobson radical of the path algebra is actually the arrow ideal in this case. Any questions so far? Okay. So as we already discussed, the set EI is a complete set of primitive orthogonal idempotents. One is equal to summation EI, and you can break it down. And as a consequence, we see that the left regular module KQ can be decomposed as the sum of indecomposable projectives PI. So PIs are, I mean, okay, this is not a consequence, as Sadanand already pointed out. We already know this, and therefore we know that PIs are indecomposable, but we also know that we can decompose any algebra like this in terms of ideals. Okay, so this is only when Q is acyclic. Yeah, we are leaving out the case when Q is cyclic because that's an infinite dimensional algebra, and we will see how to deal with them eventually. All right. And this actually tells us that these PIs, the modules PIs which Upendra defined, they are indecomposable, but this particular direct sum decomposition of the left regular module tells us that they are projectives, because it is a direct summand of a free module. I will also do a primer on projective modules eventually. For now, just bear with me. Maybe tomorrow I will do something about projective modules. If you have never seen the definition, then I will start from the basics. Okay. So now I told you at the beginning itself that we can interchangeably use the terms modules and representations. In case Q is just a quiver, we can actually prove it now. How? We are going to show that the category of representations of Q, K representations of Q, is equivalent to the category of KQ modules. Yes, Sadanand?
Yeah, so the last line of the corollary is what troubles me. See, PIs are indecomposable because EIs are primitive. How do we know EIs are primitive? I mean,
I think you first need to show that PIs are indecomposable and therefore EIs are primitive. Yes, I got the point. Yeah.
Okay.
Okay, so yeah, so I'm talking about this interchangeability between the terms representation and modules. So if you are given a representation, which recall it is simply a vector space at each vertex, and for every arrow we have a linear map between those vector spaces. So if you are given this data, then how do you construct the KQ module? Well, first of all, a module is an abelian group. But because it's a KQ module and it's an algebra, KQ is an algebra, so we have to have some kind of vector space. So the vector space is simply the direct sum of all the component vector spaces of the representation. So this is our assignment at the level of objects. On the other hand, you also have to describe it for morphisms. But yeah, sorry, before that, I should describe what is the module action. KQ is generated by paths. So I need to describe the left action of the generators on this vector space. Okay. So let us see that. So left KQ action on V is defined as this. So first of all, the zero length pass EI just acts on this tuple by projection. It just picks out one particular element. And if you have a path, alpha S alpha S minus 1 up to alpha 1, path of non-zero length, then what do? Well, if you know that alpha 1 starts at I, its source is I, then you apply the composition phi alpha S composition phi alpha S minus 1 up to phi alpha 1. So you have the corresponding definition of phi P. Yeah, the path acts by sequentially acting by the corresponding linear maps. It's the most natural way to do things. Right? Any questions about the way this module is defined? Okay. So let us see now what to do with morphisms. Once you have a morphism between representations, that is simply you have vertically some maps. At each vertex, you have a map from Vi to Wi, such that there are some commutative diagrams. But commutativity is a property, so a morphism need not preserve that property. The homomorphism, you just have to worry about the structural things here. So this tuple of FIs that gets mapped to the obvious thing, the direct sum of all these maps, or the diagonal matrix acting on all these VIs. And you can show that this functor is fully faithful and essentially surjective if you are willing to assume some set theory. Otherwise, what you can do is you can find out a functor in the reverse direction. So in case you are given some kind of some KQ module, yeah, how do you obtain the corresponding representation? Well, that is simple. You simply take the submodule generated by, no, not submodule. I'm simply acting by EI. What is it called? The action of EI on the module. I'm just going to take that. The way Upendra explained this, that was by taking home PIM. The home PIM will also give you EIM. And then what are the maps? Well, maps means you are supposed to take, let's say we have an arrow alpha from vertex I to vertex J. Then you take the entire tuple. Yeah, you take the entire tuple. Yeah, so I'm describing this. ES alpha M to ET alpha M, where alpha is an arrow, where this, let's call this I and J. And you take an element and you apply alpha on this tuple, where there is only one non-zero entry at the S alpha place. And then you act by alpha and you take the T alpha entry. This is the most natural thing that you can do. I have written it in a perhaps more complicated way. So the morphism, on the other hand, it just takes this. So here nu I is the standard inclusion and pi I is the standard projection. Okay, so nothing hard is happening. You just have to verify that these two maps are quasi-inverses of each other. These two functors are quasi-inverses. When you may not reach the same point where you started. However, you can reach something to something isomorphic. Yeah. Any questions so far? Okay, let us check your understanding and suppose I'm given, I will try to write something. Suppose I'm given some representation of A3 with this orientation, then the corresponding module will be V1 direct sum V2 direct sum V3. And what will be the action? So let me take a tuple. What will be the action of the generator beta alpha on this tuple?
It will act on x1 because source of beta
It
alpha
will
is
act on x1.
V1.
Okay. And what will be the final answer? It will act on x1. That's correct. Can you tell me the final answer?
Yeah, it's phi beta composed phi alpha
Huh?
on x1.
Yes, phi beta composed with phi alpha. Where should I write it? I need to write a tuple, a 3 tuple.
The
Yeah,
first slot is where?
First
Slot is
slot.
clear.
No. Where will we go? What is the first slot? Yeah.
Oh,
We are acting it on a tuple, right? So that's why I'm doing this exercise. See, B, what is the target of beta? 3. So therefore, we will land inside V3 by acting. So it will be 0, 0, phi beta, phi alpha acting on x1. Do you agree? Yeah. Okay. So it's simple. You just have to keep your eyes open. Yes, somebody had written an answer in the, yes. Thank you, Pawan. So we had an answer in the chat. All right. So I think you can verify this is just straightforward, and I'm not going to spend any more time with that. But instead, we are going to go to the second part. Yeah. So how will we deal with the situation when we have directed cycles in the quiver? Let's say we know that we'll get an infinite dimensional associative K algebra, but sometimes we are actually interested in some algebras which are finite dimensional. So we have to take a quotient. Well, let me start with one particular example. So this particular algebra is interesting in analysis or even geometry. K epsilon by the modulo the ideal generated by epsilon square. Here you should think of epsilon as an infinitesimal. And when you are doing computations with infinitesimals, you obviously kill its square or any higher power. So you are only left with something containing, like, it will be a two-dimensional vector space where there will be a constant term and some multiple of epsilon. Epsilon, like infinitesimals, are already small, so we can ignore all its higher powers. Yeah, that's the idea. So if we want to deal with this situation, well, we have a corresponding, it's a finite dimensional algebra, and we have this alpha with one vertex. This is a loop quiver, if you remember. But then the idea is to kill alpha square. We declare that this particular path was 0. Okay, so how to do that? Yeah, algebraically, we still have to do something. Heuristic answer is that kill some power of each cycle, but maybe there are too many cycles. Yeah, so how to algebraically manipulate the situation? So we say that a two-sided ideal of the path algebra is an admissible ideal if it sits inside the square of the radical, square of the arrow ideal, and some finite power of the arrow ideal sits inside I. Why we are doing this, it will be clear very soon. The pair Q comma I is called the bound quiver, and the bound quiver algebra associated with this bound quiver is this finite dimensional algebra KQ mod I. So as you can see with L1, and I take the ideal generated by alpha square, the path alpha square. So if alpha square is killed, then of course alpha cube, alpha to the power 4, all higher powers are killed. So KL1 is basically this, yeah, KL1 modulo the ideal generated by alpha square is isomorphic to the algebra that we were interested in. Okay, so now why this sandwich between two powers of the arrow ideal? So first of all, observe that if Q is acyclic, yeah, then this finite power is automatically contained in the ideal, because as we discussed, if Q is acyclic, then the arrow ideal is nilpotent. So some power is 0, and 0 is contained inside every ideal. So we don't have to worry about what we are like, only this condition 1 is sufficient. The point of taking 1 is that no lazy path or an arrow is killed by the ideal. If we are treating this, I mean, it's not that you can't do it, but if we are treating that quiver as the set of like the source of generators, then why would we kill some vertex, some lazy path or an arrow? If we wanted to kill that arrow, we might not as well have drawn it. Yeah, that's the philosophy behind including I inside the square of the arrow ideal. We don't want to include anything in the first power of the ideal. Okay. And finally, because some power of the arrow ideal is contained inside I, we know that KQ mod I is finite. Because it is quotient, it is a quotient algebra of the algebra KQ mod RQ to the power M, which is a finite dimensional algebra. So in order to make it finite dimensional, the second condition is necessary. And to ensure that the quiver remains intact, the first condition is necessary. So an admissible ideal is this way sandwiched between two powers of the arrow ideal. Any questions so far? Okay. Fine. So normally, I mean, we do not give this like how do we write this ideal? We have to
So
write
how
it
you
in Dibyendu?
so how you write the Jacobson of that KQ mod I? So you can write it using RQ right?
Jacobson
KQ
radical
mod
of what?
I. KQ mod
KQ
I.
mod I. Yeah, that will be RQ mod I.
Okay. Yeah. Thanks.
So, yeah, how do we describe this ideal? Yeah. Well, we have to describe it using certain relations between paths. So, for example, as I already described, well, I can decide to kill off some power of some or some path, or I can also have something like this, yeah, that alpha square is same as alpha cube, and I can quotient out KL1 by this. Whenever I see alpha cube, that is nothing but alpha square. Or if you want, you can also write -2 alpha cube. You can talk about anything like this. And such things are relations, but there is a proper terminology for relations. So for example, yeah, I mean, let's go back to this Kronecker quiver. Yeah, by the way, I think I did not mention yesterday. So Kronecker died before 20th century. Yeah, so he was in 19th century, he was studying pairs of matrices up to simultaneous conjugation. Yeah, pairs of n cross n matrices up to simultaneous conjugations, and that's why these kinds of quivers are named after him. Yeah, okay, so Kronecker quiver. So in this also we can describe the relation that alpha is equal to phi beta, which means alpha minus phi beta is equal to 0. So what is a relation for us? So let me ask you, yeah, does this make sense? So alpha minus phi beta is one kind of relation. Then another relation is alpha minus E1 plus E2. Which ones do you think should be allowed? Alpha minus phi beta should be allowed or not?
If you want homogeneity, then the first one. Maybe.
Homogeneity, then the first one, yes, correct. And the second one doesn't make sense because their source and targets are different. Yeah, the linear combination that we are considering, linear combination of paths, they should have the same source and same target. Otherwise, we can simply separate them out. We can find smaller relations. So that's what I have written here. A relation on Q is a finite k-linear combination of paths with the same source and same target. All those paths should share the same source and target. Okay? So, right. And how many relations are necessary? Yes, Sadanand?
Yeah, so in this, as Irfan told, are we always assuming homogeneity, or this I
No, no,
is
no,
this
no.
I
We
homogeneous idea?
see, basically, if that were the relation, yeah, alpha minus E1 plus E2, then actually we are saying three different things. The coefficient of alpha should be 0, coefficient of E1 should be 0, coefficient of E2 should be 0. We are saying those three different things. So we can break that particular expression in the form of three independent relations. So we are trying to find generators of this admissible ideal. And the generators are these relations. So our best way is to go via relations, and they should share same source and target. We are trying to find nice generators. Yeah, that's all. Okay. So this admissible ideal. Now,
I'm sorry.
yes.
I'm sorry
Okay.
for stopping you again. So we were saying individually the coefficients are 0 because those forms a basis, and you were equating it to the 0 element, and the individual basis has to be 0. Is that the reason, or no?
I mean,
I don't.
no. See, we are just trying to break it down as per source and target. That's all. For niceties, maybe. Yeah.
Okay.
You can obviously say the ideal generated by alpha minus E1 plus E2 is 0, but that can be written as the ideal generated by alpha, comma, E1, comma, E2.
Okay.
Okay. So, is this ideal finitely generated by these relations or not? Well, the answer is it is finitely generated because our quiver is finite. So, why is it finitely generated? Because you have to use that I modulo r to the power m is an ideal of a finite dimensional algebra kq mod rq to the power m. Okay, I think I forgot to mention this q over here. Let me add those things up over here. And so because it's an ideal of a finite dimensional algebra, it is finitely generated, and RQM is obviously finitely generated. And then there is this exact sequence of modules which tells you that I is also finitely generated. So every admissible ideal is finitely generated. You can write down finitely many relations and you will get it. Now, before I proceed, yeah, I would like to give you an answer, or maybe you should give me an answer about how to express this particular algebra that we left out, the polynomial ring in two commuting variables, polynomial algebra in two commuting variables. What relation should we choose?
The same one, x, y, my, I mean,
Xy minus yx. Okay, thanks, Thomas. Okay, thanks, Sadanand, as well. Xy minus yx. Yeah, that is a relation. We are talking about the loop quiver L2, and xy and yx are both paths with the same source and target, and xy minus yx is a relation. We put that and we get this.
Yes,
Again,
excuse
it's
me.
not finite dimensional. Yes, Irfan?
Just out of curiosity,
Uh-huh.
by any means, do we get this kxy from A2?
Kxy from A2, no. A2 will be finite dimensional. It will be a matrix algebra, either upper triangular or lower triangular 2 cross 2 matrices.
Okay, maybe. Oh, right. You have
It's
to
a three-dimensional
loops.
matrix. Yeah, A2 will give you three-dimensional algebra, whereas Kxy is an infinite dimensional algebra.
True. Thanks. Yeah.
Okay. Okay.
Uh,
However,
I have
okay.
one more dumb.
Uh-huh.
This might be dumb. Like, shouldn't it be
No
then
question is dumb.
so shouldn't it be like KQ mod I finite dimensional, which makes KXY is finite dimensional, which is absurd.
No. I'm not saying
Right?
that.
Is that
I'm not
an
saying that.
admissible?
I'm not saying it's
In,
an admissible ideal. It's not an admissible ideal. That's why I did not say it's an example of this.
okay.
Why is it not an admissible ideal? That's actually a good question, because no power of the arrow ideal is contained inside it.
Okay.
It's an infinite dimensional algebra, but no power of the arrow ideal is contained inside it.
So that's not a bounded quiver algebra.
So it's not bound quiver algebra. It's infinite dimensional. Yeah, bound quiver algebra is always finite dimensional.
Okay.
Okay, thanks for the question, actually. Yeah. Okay, so now just remember that we haven't yet answered what to do with the matrix ring. Dipendu answered that question in the beginning, that it's Morita equivalent to something else, but we have to see that slowly. Okay, so there are two important things which are independent. So say that an algebra is connected if 0 and 1 are the only central idempotents. Okay, there is no other non-trivial idempotent which is central, which commutes with every other element. And this connectedness of an algebra is obviously related to connectedness of the quiver. So Q is connected as a graph. Yeah, I'm not saying I mean, there should be a zigzag of arrows between any 2 points. The underlying graph, undirected graph, should be connected. So the underlying graph of Q is connected if and only if KQ is connected. If and only if, I mean, this one also we are saying, because we are taking an admissible ideal, so the quotient, this KQ mod I will also be connected. Okay. Fine. So how to obtain this complete set of primitive orthogonal idempotents for the bound quiver algebra? Well, that will be EI plus A. Sorry, EI plus I, where I is the admissible ideal. You simply take the images, the corresponding cosets of the original primitive orthogonal idempotents. Now, again, there are some certain things I'm sweeping under the carpet. Okay, so Now comes an important definition that an algebra with a complete set even e to en of primitive orthogonal idempotents is a basic algebra if it satisfies this condition. Take the left ideal generated by EI and the left ideal generated by EJ. If they are isomorphic, then it should imply that I and J are equal. Okay, so if this condition is satisfied, then we'll say it is basic. So if it is not, then what can we do? Well, from each of these equivalence classes, we define this equivalence relation. If AEI is isomorphic to AEJ, then we put both those idempotents in the same equivalence class. And we choose a representative set of these equivalence classes. And that is what I'm calling here by denoting by J naught over here. And we can form this new thing. Yeah, EA is the sum of these representative, the class of representative idempotents. Yes, Sadanand?
Are you assuming that complete set is also orthogonal or not?
Yes, I'm assuming orthogonal. I did not write it, but yeah. Completeness, I think in my mind when I was writing this, it's orthogonal. Yeah. Maybe I should write it for, because you have a question. So orthogonal, yeah. Okay, so we have formed this new element right now. EA is the sum of these representative idempotents. And we are going to define a new algebra with this. So the basic reduction of A is this algebra AB, which is EA, EA. So you are multiplying by EA on both sides. Whatever this algebra is, yeah. So what happens, why is it important that every finite dimensional K algebra is Morita equivalent to its basic reduction? So AB is of course an algebra. It is a finite dimensional algebra and it is basic because we are choosing only one idempotent from each equivalence class. So of course there are certain things to be proven here, but it is a basic algebra. Take my word for it. And what happens is this interesting thing. Morita invariance, the technical definition is complicated. I mean, it basically talks about how these two categories are equivalent. It describes the functor in terms of a certain bimodule. But let us simply say that if these two categories are equivalent, then these two algebras are Morita equivalent. So their module category should be equivalent. That's all. And that's our result. So therefore, every algebra is Morita equivalent. So which means what? Yeah, we are interested in studying representations. But representation is an equivalent thing as module. So if we are only interested in studying modules, then we may as well study only basic algebras. If now also recall, yeah, I'll not go any further before talking about this. Also recall that what is the notion of connectedness? Connectedness means that only 0 and 1 are central idempotents. No other central idempotent exists. So if you remember, I talked about this particular result over here. If you have any other central idempotent, then you can actually decompose that algebra as a direct sum of two algebras. So therefore, what I'm saying here is it's enough. If you want to study representation theory of finite dimensional algebras, then it is enough to study representation theory of connected basic algebras. Any objections or comments about this? Okay, yes.
how do we find that maximal set? There may be several such things, right? I mean,
Yeah, but you can choose any representative, basically any representative of idempotence. Yeah.
okay. So any sub-collection, any
Any
maximal sub-collection.
subcollection, there are two properties, right? Any subcollection such that it intersects every equivalence class and in exactly one idempotent. Yeah. Okay. But so far we haven't really seen. I mean, this
Thanks.
result. Huh?
Nothing, thanks.
Okay. So this result only reduces the job of studying representation theory of finite dimensional algebras to that of finite dimensional basic connected algebras. But where are quivers coming into this picture? Well, here is the construction, and that will complete our search. Yeah, so this is the so-called Gabriel quiver. So Gabriel described this for a basic finite dimensional K algebra A. So its vertex set, yeah, is the complete set of primitive idempotents, primitive orthogonal idempotents, if you want. I'm assuming that in the definition of completeness itself. And what are the arrows? How many arrows do you draw from one particular idempotent to another idempotent? So these, you simply have to take the dimension of this particular space. What you are doing? Well, E prime JA mod J square A. You understand this? JA is an ideal, so JA mod J square A. J square A is smaller, and then E. So this particular vector space, you have to take the dimension of this vector space, and that will give you a quiver, and a quiver with maybe I'm missing something here. I think I will maybe describe it next time, what to do with relations. We obviously have to talk about relations, and I missed that part completely. I'll describe the relations. And then our goal one will be complete. So what this particular construction is showing, construction followed by a theorem which says that whatever quiver with relations you have constructed, the bound quiver, then the bound quiver algebra is isomorphic to the given algebra. Okay, so therefore it is sufficient to study only bound quiver algebras. If you remember, that was our goal.
Hello.
Yes, Dibyendu?
So from arrows E to E dash, you are saying it's
Uh-huh.
corresponds to I mean, that will be, why not E first and J mod J square E dash? Why I mean, is this a notation something, or there is something else?
You are taking multiplication on both sides by these elements. You take the collection of all such things, all such elements. That will be an algebra because these are idempotents on both sides.
No, so you can take also E J mod J square E dash also, right?
Oh, I think I made a choice because of the way I'm writing, because of the way I'm writing the multiplication.
Okay.
I'm following exactly the opposite convention of Schiffler for writing paths.
Okay.
Because I'm used to this particular way of writing things. Okay. Yeah, and if you simply swap the positions of E and E dash, what will you get? You will get the opposite quiver.
Yeah, opposite quiver.
Yeah, so I mean, you are not very far from where you were.
Okay.
Okay.
I have a doubt.
Yes, Tirtharaj.
So first of all, are you constructing this Gabriel quiver for connected basic five dimensional algebras?
No, it's not necessary. If I don't start with a connected algebra, then I will get a disconnected quiver.
Yeah. Okay.
Uh-huh.
And okay, so the goal one is you're constructing this Gabriel quiver along with a admissible ideal, and that the quotient will turn out to be isomorphic to
Yes,
be.
yes,
Okay,
correct,
okay,
correct, correct. Yeah.
okay.
I have missed that part and I will perhaps fill it up tomorrow and then I will show you. Okay. So what about the representations of bound quivers? We haven't defined them so far. We only know what is the concept of representation of a quiver. What about bound quivers? Well, this is the definition that you take a representation of the quiver, and whenever you have some relation in some element in the ideal, then the corresponding element in the algebra should be 0. I should say that whenever you start with some relation, then for that relation, this particular quantity in that vector space should be 0. In an appropriate vector space should be 0. So phi p is the notation, which is the iterated application of phi, like phi alpha is composed with phi alpha s minus 1 up to phi alpha 1. In an appropriate vector space, you will get 0. So we have to put this extra condition. So basically what we have is a subcategory of the category of K representations of Q. It's a subcategory. And on the other hand, what we have, well, we have KQ to KQ mod I. Yeah, there is a corresponding surjection, natural surjection map from an algebra to its quotient. And that natural surjection map gives you a restriction of scalars. So therefore, KQ mod I, like the bound quiver algebra modules, will give you some quiver algebra modules. Yeah, I mean, so on both these sides, you actually have this restriction. And this equivalence that we already had in the bottom row, that equivalence restricts to an equivalence between these two new categories. So the the modules over the bound quiver algebra are like the category of that is equivalent to the category of representations of the bound quiver. So we don't really have to do anything extra over here. Yeah, just the original equivalence itself will restrict to an equivalence appropriately. Any questions? Okay. Okay, then what about these projectives and injectives? Well, I'm just going to introduce these notations here. What do you do with the projective module? Well, projective modules over this are these representations. So Pij phi alpha, same thing. But what is Pij? It is the vector space with basis P plus I, where P is a path from I to J. So it could be that this particular path is killed by the ideal. This P belongs to the ideal, or some subpath of it belongs to the ideal. In that case, that won't contribute to the basis. Yeah, so a priori, we cannot count the dimension unless you know the ideal very well. Okay, and the rest of the things will remain the same. What is phi alpha? Phi alpha is the composition with alpha, which means phi alpha p plus I acts as alpha p plus I. Whenever possible. Yeah, alpha p with I plus I. And again, what you will have is this pi in this new setting is the ideal generated by this new primitive idempotent. Ei plus I is the new primitive idempotent, and it is the left ideal generated by that. And dually, the injective module is the right ideal generated by this. Any questions? Like, I'm going to change the topic for some time. Okay, maybe I should do some kind of, I should take stock. Yeah, what we have shown so far is that even though there are finite dimensional algebras in different varieties and forms, every finite dimensional algebra can be is Morita equivalent to a bound quiver algebra in one line. So it is sufficient to only study the representations of bound quivers, and that was our goal one. For infinite dimensional algebras, we are not making any such claims. Yeah. However, if you are interested, you can also study them. And why quivers? Because quivers are interesting diagrammatic pictorial ways of encoding the generators and the relations, generators and relations. Yeah, now the word relation has also been made clear. Relations are finite k-linear combinations of paths sharing same target and source and target. Okay. If you have any questions, then just ask me. Otherwise, we'll proceed. So this was the presentation aspect. So goal one, we have seen. Modulo, I describe how to obtain those relations. Goal two is something that we are going to start looking at now. So yesterday we described what irreducible morphisms were. And in the Auslander-Rayton quiver, we said that we have to take how many arrows between two isomorphism classes of indecomposables. That is the maximum number of linearly independent maps. Yeah, but that definition doesn't really make sense. We want to find the skeleton of the module category, but that definition is incomplete so far. So we have to go via this method. We are going to start studying the radical of the module and thereby define what, how to count these number of irreducible morphisms or the number of arrows we put in between. So remember, what is the radical? Well, radical definition we wrote here. Jacobson radical, what was the definition? We are going to be interested in this particular definition. Yeah, the third one or fourth, the number 3, that for all B in A, the element 1 minus AB is a unit. This is an equivalent condition for an element to belong to the Jacobson radical. Okay. But I'm sure that you will find this definition interesting by itself. So what is the next thing to do? Given a finite dimensional K algebra, say that a class I of morphisms in A mod is an ideal. Well, this is just modeled on the usual definition of ideals of a ring. What are the two conditions? It should be a subgroup. Then it's a two-sided ideal. So it should be closed under multiplication by ring elements on either side. Okay, so let us see. A class I of morphisms in A mod is an ideal if, well, I'm defining a new notation. IMN is the collection of those morphisms in the collection I, whose source is M and target is N. Which go from M to N. That's all. So I'm claiming that this is a K subspace of home Mn. Home Mn is the collection of all morphisms. So I want it to be an abelian group. But now the condition will be locally an abelian group. Usually when we talk about categories, then the word local refers to the home sets. Yeah? So in home sets, it is a subgroup. Well, not just subgroup, but I'm saying something more because we are not talking about rings. We are talking about algebras. So I'm saying it's a K subspace. It's also closed under scalars, and it is closed under addition. And it has 0. So 0 between any two modules also lies in this ideal. And this is the second condition, that whenever you have a triple of composable morphisms and the middle one belongs to the ideal, then so does the composition. Okay, so multiplication here is replaced by composition. Multiplication is composition. And in particular, I'm saying that it is a left ideal as well as a right ideal, because I can always choose G to be equal to identity. So therefore, HF will be in I. Or I can choose H to be an identity, so FG will be an I. So I'm declaring both conditions simultaneously. I believe that many people, even working who work in algebra, they don't know this definition. The ideal of a module category. So this is an ideal, and you have different properties of ideals. You can do arithmetic, you can take intersection of ideals, you can also take products of these ideals, and we will see something. Okay, so an ideal contains a split map, which means a map with one-sided inverse if and only if it contains every single morphism. Well, perhaps I need to show you a proof. Yeah, so let us see. Suppose F belongs to I and F is a split mono. I.e., well, what I'm saying is this. There exists a G such that GF is equal to identity. Identity on the source. Yeah, let me call it from M. F is from M to N. Identity on the source. Well, then what happened? Because of right multiplication property and left multiplication property, so therefore 1M belongs to the ideal. So I have concluded that one isomorphism, if there is a split morphism, then one isomorphism belongs to the ideal. And as soon as this isomorphism is there, so I can conclude that any F is in there. Any F with that source is there. Any G with source M is there. It is also there. You have to, you can see the rest of the proof. Yeah, it's very simple. So an ideal, if it is a proper ideal, then it should not.
How about maps from other objects?
Maps from other objects. Yeah.
Which does not have any role of M and N involved. I mean,
maps
let's say P
other
to Q.
objects.
H, a map from P to Q. How do we know that H belongs to I?
Okay. So, I mean, this way you can just give me a moment. Yeah, let me switch on the fan. It's getting very warm because it's afternoon. Right. So you are saying if M and N is not there, you take any Z. Yeah. So we have concluded that any object which any morphism which has endpoint at M, it is there. Now you take any Z, and you take home MZ and home MZ and home ZM, they are there. Okay. Okay. What am I saying? Oh, no. I think I'm making a mistake here. Even if locally we have that,
Sir, would it perhaps be fine to say that IMN would be
IMN would be home MN, yes. Who was talking?
sir, it was me, Daksh.
Daksh. Okay, yeah.
Can you hear me? Yeah.
Yeah. So IMN would be home MN and INM would also be home NM for every N. And other morphisms should also be there. The identity morphism is there. Okay, I've done this proof. Okay, I'm not going to spend any time on this right now. I will tell you tomorrow if what I'm saying is correct or not. I have 7 minutes left. Okay, so the radical of the module category now, yeah. This module category of finite dimensional modules only. We are not talking about the whole thing. I'm describing it to be the class of, by describing the class of morphisms from M to N. And these are all these morphisms F such that 1M minus GF is an isomorphism for each G in home NM. Now here, that third condition that I showed to you earlier, that comes into picture. For all B, 1 minus BA is a unit. Unit means what? Well, in this case, it's an isomorphism. Well, which isomorphism? Well, yeah, I mean, I'm just saying it's an isomorphism in the endomorphism algebra. Okay. So, well, what will happen in this case, in the case of this radical? If F is an isomorphism, then 1M minus F inverse F is not an isomorphism because it is 0. If F is an isomorphism, then F inverse F is identity. So 1M minus 1M is 0 and 0 is not an isomorphism, and therefore an isomorphism does not lie in the radical. Do you all agree with this? That an isomorphism is not in the radical. So units are not there. But we can say something more. Yeah, so these are 3 properties. So the radical, okay, so first of all, you have to go through a proof that the radical is indeed an ideal. Right now, it's simply a collection of certain morphisms, but then you have to prove it will require some tricks, but the proof is very long. So I'm not going to cover this proof. I can give you a reference nevertheless. So that is lemma 7.5 in Schiffler's book. You can read the proof if you are interested in it. So the radical is indeed an ideal. And the radical, the endomorphism of the radical, rad MM is actually the radical of the endomorphism algebra. That proof is actually very simple because of what we just saw. Yeah, because it's a local algebra. So what is something like in terms of local algebra, what is the condition? That every element is either a unit or 1 minus A is a unit. So therefore, this you can easily see to be the radical of the endomorphism algebra. Because 1 minus GF is an isomorphism for every G. So in particular, 1 minus F is an isomorphism. So F is not an isomorphism. F is not an automorphism, I mean, automorphism of N. The third one is something that I wish to do here, that if M and N are indecomposable, then rad Mn is the collection of all non-split morphisms. Yeah, this will pave a way to counting the basis of irreducible morphisms. Okay, so let me write some proof of this. So the statement is this, that radical A of Mn is equal to all those morphisms in home AMN such that F is non-split. And here we are assuming that M and N are indecomposable.
Can you please recall the definition of non-split ones?
Of non-split. Yeah, so it doesn't have one-sided inverse. It's not a split mono or a split epi.
Okay.
Okay. So rad Mn is the collection of all non-split morphisms between these two. Now I'm going to show this side first. This side is contained in this side. Well, we know that an isomorphism is not in rad Mn. That's easy to see. I mean, I just argued for you that an isomorphism is not there. And well, what can be a split mono between indecomposables? See, if F from M to N is a split mono, then what happens? Then there exists, yes, N isomorphic to N dash direct sum N double dash such that N dash is isomorphic to, yeah, maybe N dash is, image of N dash is equal to the image of F. So what I'm saying is this, that it will be an isomorphism to N dash direct sum N double dash, and N double dash plays no role whatsoever. What can this N double dash be? The only choice is 0. It's an injective map, so it can be 0. That's all. Okay, so N dash, so which means because it's indecomposable. And that's all. So it can't be a split mono unless it is an isomorphism. It can't be a split epi unless it is an isomorphism. So we have shown that rad actually is contained inside all these morphisms. For the other one, the proof is a bit long, and maybe because it's already 3:31, we will open with that proof for the reverse inequality next time. Any questions? Okay, so see, I'll tell you what we are planning to do tomorrow. We will define powers of this radical, all ordinal index powers of the radical, and then we will prove this important result, that a map is irreducible if and only if it belongs to radical but not its square. And therefore, the arrows that we are counting is just rad modulo rad square. That is the definition. Yeah, this is the definition of Auslander-Eiten quiver. And that will complete goal 2. And then we will proceed with a primer on projective and injective modules resolutions and some bit of homological algebra.